This video includes information on the pH scale.
Water reacts with as an acid when it reacts with a base. So if ammonia is our base and it reacts with water, water is acting like the acid. But water can also react as a base with an acid. If we were to take hydrofluoric acid and add it to water, now the water is going to act like a base. So water can act like an acid and it can act like a base. It depends on what it's reacting with. And we call substances that can either accept or donate protons amphoteric. So water, because it can act like an acid and it can act like a base, it's an amphoteric substance. And what determines whether it acts like an acid or a base? What it's reacting with. Autoionization is a reaction that takes place when two molecules react with each other. Water can autoionize. So if we have two water molecules, two like molecules, and we react them together, it's kind of hard for us to say which is the acid and which is the base. But when we write it, we can figure that out because we've got water here that's acting like an acid. So it's going to donate a proton. And we have a water molecule here that's going to act like a base and accept that proton. So when water acts like a base and accepts a proton, it forms hydronium, which in the reverse direction is the acid. And when water donates a proton, it's acting like an acid and it forms hydroxide, which is the base. And we could rewrite it like this instead of writing the Lewis structure. So we've got water reacting with water. That's an autoionization when two molecules that are the same are reacting. We produce hydronium and hydroxide. Now, it's a reversible reaction. We can write a K expression. And we give the K just a slightly different look to it. We use a subscript W to say we're talking about the equilibrium constant for water, Kw. And we calculate Kw the same way we calculate any equilibrium expression. It's the concentration of the products over the concentration of the reactants raised to the power of the coefficient in the balanced equation. But remember that liquids and solids are not included in K expression. So water would not be included in our K expression. So Kw equals the concentration of hydronium times the concentration of hydroxide. So this is our Kw expression. Kw is an equilibrium constant. It's called the ion product constant for water. And at 25 degrees Celsius, Kw equals 1.0 times 10 to the minus 14. Now remember that all K values are temperature dependent. If we change the temperature, we change the value of K. But at 25 degrees Celsius, Kw equals 1.0 times 10 to the minus 14. It's a constant. Autoionization of water produces hydronium and hydroxide. We're at equilibrium. Kw equals 1 times 10 to the minus 14. If we were to look at pure water, the concentration of hydronium ions will equal the concentration of hydroxide ions because it's a 1-to-1 ratio. If we don't know what these concentrations are, we could say they're X. So hydronium is X and hydroxide is X. That that means kW equals x squared. Well, kW is a constant, so we can plug in 1 times 10 to the minus 14 in for kW. So 1 times 10 to the minus 14 equals x squared. If we take the square root of both sides, we're going to get x by itself. And x equals 1 times 10 to the minus 7, which is the concentration of hydronium ions and the concentration of hydroxide ions in pure water. So that's something we want to remember. Okay, the concentration of hydronium and the concentration of hydroxide in pure water is 1.0 times 10 to the minus 7. If we add an acid to water, that's going to change the ratio of hydrogen to hydroxide. Or if we add a base, it's going to change the hydrogen or the hydronium to hydroxide concentration. And we're going to now look at solutions that are acidic, neutral, or basic in character. So if we look at a neutral solution, the concentration of hydronium equals the concentration of hydroxide, and we calculated that value to be 1.0 times 10 to the minus 7. If we have an acidic solution, it means that we've increased the hydronium ion concentration. Well, if we increase the hydronium ion concentration, that's going to decrease the hydroxide ion concentration. So by definition, the hydronium ion concentration is greater than the hydroxide ion concentration in an acid. And the concentration of hydronium ions will be greater than 1.0 times 10 to the minus 7 in that acidic solution. Now, if we have a basic solution, we're increasing the hydroxide ion concentration, which would decrease the hydronium ion concentration. So a basic solution, the hydronium ion concentration is less than the hydroxide ion concentration. So the hydronium ion concentration will be less than 1.0 times 10 to the minus 7. Kw equals 1 times 10 to the minus 14 equals the hydronium ion concentration times the hydroxide ion concentration. Since Kw is a constant, if we know the hydronium ion concentration, we can calculate the hydroxide ion concentration. And if we know the hydroxide ion concentration, we can calculate the hydronium ion concentration. Okay, so let's look at a couple of practice problems. Calculate either the hydronium ion concentration or the hydroxide ion concentration for the value you're given, and decide whether it's an acid, a base, or neutral. So it tells us that the hydroxide ion concentration equals 1.0 times 10 to the minus 6. Well, if we know the hydroxide ion concentration, we want to calculate the hydronium ion concentration. And then once we calculate that, we can decide whether the solution is acidic, basic, or neutral. Okay, well, how do we do that? Well, we know that Kw equals the hydronium ion concentration times the hydroxide ion concentration. If we want to figure out the hydronium ion concentration, we would divide both sides by the hydroxide ion concentration. So the hydronium ion is Kw divided by the hydroxide. So 1 times 10 to the minus 14 divided by 1.0 times 10 to the minus 6 will give us our hydrogen ion or hydronium ion concentration. Remember in the calculator, 1 EE negative 14 divided by 1 EE negative 6. And we should get 1.0 times 10 to the minus 8. Now, this one we could actually do without a calculator. 1 divided by 1 is 1. And if we divide with exponents, we're subtracting. So negative 14 minus negative 6 gives us that negative 8. You're always going to have a calculator, so you don't necessarily have to do it in your head. But if the number is 1.0, you could actually figure out the concentration without a calculator. Now, since the hydronium ion concentration is less than 1.0 times 10 to the minus 7, it's a basic solution. The hydronium ion concentration is less than the hydroxide ion concentration. That's what makes it a basic solution. The next one, we can't do in our heads because it's 2.35 times 10 to the minus 9. But modeling what we did up here, if the hydroxide ion concentration is 2.35 times 10 to the minus 9, calculate what the hydronium ion concentration would be. Okay, so work it out. Use your calculator. And then once you do that, once you figure out your hydronium ion, figure out whether it's acidic, basic, or neutral. All right, so let's see how you did. Kw, that's always 1 times 10 to the minus 14, divided by 2.35 times 10 to the minus 9. So in the calculator, 1e negative 14 divided by 2.35 e negative 9. And you should get 4.26 times 10 to the minus 6. Now, the hydronium ion concentration is greater than 1 times 10 to the minus 7. That makes it acidic. Or we could say that the hydronium ion concentration is greater than the hydroxide ion concentration. That makes it acidic. 10 to the minus 6 is bigger than 10 to the minus 9. Does that make sense? You have a lot more zeros in 10 to the minus 9 than you have in 10 to the minus 6. Now, for this one, you're given the hydronium ion concentration. Okay, you want to calculate the hydroxide ion concentration. You're going to do it the same way. Okay, we've got our Kw expression. This time we want to calculate hydroxide, so we have to divide both sides by hydronium. Okay, and we modeled how you want to show your work. So when you're doing it in your notes, do it the same way so that you have it as a reference for when you do your homework or when you're doing your labs or when you're studying for your test. Okay, the more work you show in your notes, the easier everything else is going to be. So Kw divided by hydronium will give you hydroxide. Okay, so 1 times 10 to the minus 14 divided by 8.60, agreed, is 1.16 times 10 to the minus 15. Now, this number is significantly less than this number. The hydronium ion concentration is much bigger than the hydroxide ion concentration, and that's what makes it an acidic solution. So if you're given the hydronium ion concentration or the hydroxide ion concentration, and you're asked to solve for the other one, this is the equation you want to use. This is how you relate hydronium to hydroxide. Let's talk about how that's related to pH, which is probably familiar, and pOH, which is not as familiar. So we can talk about the acidity of a solution by talking about the concentration of the hydronium ion. But those are kind of awkward numbers to look at. It's more convenient, it's easier if you talk about it in terms of pH. So how do we relate concentration and pH? Here's our equation. pH is calculated by taking the negative log of the hydronium ion concentration. So if you're given the hydronium ion concentration and asked to figure out the pH, negative log hydronium gives you pH. pOH is in terms of hydroxide. So pOH is the negative log of the hydroxide ion concentration. We know this equation already. Okay, Kw equals our hydronium ion concentration times our hydroxide ion. And we know that Kw equals 1 times 10 to the minus 14. Okay. If we increase the hydronium ion, it would have to decrease the hydroxide ion. If we increase the hydroxide ion, it would have to decrease the hydronium ion, since the product is always this number. Now, we're going to do a little bit of math with this equation. Oops. We're going to take the negative log of both sides. We can do that. As long as we do the same thing to both sides of an equation, it keeps it equal. So if we take the negative log of both sides of this equation, the negative log of 1 times 10 to the minus 14 is 14. So 14 equals the negative log of the hydronium ion plus the negative log of the hydroxide ion. Now, the negative log of the hydronium ion we defined as being pH. And the negative log of the hydroxide ion we defined as being POH. So that gives us another equation to work with. pH plus POH will always equal 14. Okay, so we have an equation to calculate pH. We have an equation to calculate POH. We have an equation to relate hydronium to hydroxide, and we have an equation to relate pH to POH. All right, so let's work with that a little bit. For a solution in which the hydronium ion concentration is 1.0 times 10 to the minus 3, calculate the pH and the POH. All right, well, we're given the hydronium ion. We can calculate the pH. Oop, I shouldn't do that. The negative log of the hydronium ion concentration will give us the pH. And once we know the pH, if we subtract it from 14, that'll give us the POH. So pH is calculated by taking the negative log of the hydronium ion. So in this case, the negative log of 1.0 times 10 to the minus 3. Now, because it's a log function and this number is 1, the exponent is going to be our pH. So the pH is 3. Now, to calculate the POH, we would take 14 and subtract the pH, and we calculate the pH to be 3. So the POH is 11. Now, let's look at significant digits for a minute. When we look at pH or POH, the number of decimal places in that value is determined by the number of significant digits in the concentration. So since 1.0 times 10 to the minus 3 has 2 significant digits in it, the pH is going to have 2 decimal places. Now, when we go to figure out POH, 14 is an exact number. We're not going to use that to figure out how many significant digits we have in our POH. But we're going to subtract 3.00 from that. And subtraction, we always look at how many decimal places we have to decide how many decimals we want in our answer. So since there are 2 decimals in our pH, we want 2 decimals in our POH. So let's kind of sum this up. If we were to look at an acid, an acidic solution is anything in which the hydronium ion concentration is greater than the hydroxide ion concentration. And that's going to give us a pH less than 7. And the farther away from 7 we get, the larger the hydronium ion concentration is, and the smaller the hydroxide ion concentration, and the more acidic the solution is. If we're looking at a neutral solution, the concentration of hydronium equals the concentration of hydroxide. And we already calculated that the hydronium ion concentration in a neutral solution is 1 × 10⁻⁷. So the pH is 7 for a neutral solution. If we have a basic solution, the hydroxide ion concentration is bigger than the hydronium ion concentration. And since the hydronium ion concentration is now less than 1 × 10⁻⁷, the pH is going to be greater than 7. And the farther away from 7 we get, the bigger the pH is, the lower the hydronium ion concentration is, and the more basic the solution is. So that kind of summarizes up the relationship between the concentration of hydronium and the concentration of hydroxide, how that's related to pH, and the type of solution we're looking at. We don't have to memorize any of this, but just to give us a little bit of an idea here. Okay, we have pure water kind of in the middle here. If we're looking at a solution that's acidic, the hydrogen ion concentration is going up, while the hydroxide ion concentration is going down. And the bigger the hydroxide ion concentration, the smaller the pH and the more acidic the solution is. Now, on the other side, if we decrease the hydronium ion concentration, we're going to be increasing the pH, which would make the solution more basic. Okay, so that's just a kind of relative thing. So if we look, rainwater is a little bit acidic, stomach acid is more acidic, hydrochloric acid, 1 molar, is even more acidic. On the basic side, blood is just a little bit basic. Ammonia is much more basic, and 1 molar sodium hydroxide is even more basic. How can we measure pH? Well, we could use a pH meter, and that would actually give us a numerical value for the pH of the solution. But we could also use pH paper. And maybe if you have a pool in your backyard or you have a fish tank, you may have used some form of this pH paper where you dip the paper into the solution, and then you compare the color to figure out what the pH is. Or you could use indicators. And indicators are just different types of solutions that change colors depending on what the pH of the solution is. So different ways that we can either measure or estimate the pH of a solution. All right, so let's do a couple of problems. Okay, see if we can kind of tie all this together before we move on. A sample of orange juice has a hydronium ion concentration of 2.9 × 10⁻⁴ molar. Calculate the pH. Okay, so let's just do that question first. You're given the hydronium ion. You want to calculate the pH. Now, keep in mind, there are 2 significant digits in your hydronium ion concentration. So you're going to want 2 decimal places in your pH. So we're going to take the negative log of 2.0 E -4. Since there's 2 significant digits here, we want 2 decimal places in our pH. So 3.54. And that makes sense. If this was 1 × 10⁻⁴, the pH would be 4. The bigger this number gets, the farther away from 4 and the closer to 3 it gets. It's a log function. All right, so let's look at the second one. We have some stomach acid. Okay, we're told that the hydronium ion concentration is 1.20 times 10 to the minus 3, we want to calculate the pH of stomach acid. So go ahead and calculate the pH for stomach acid. Now, think about significant digits. There are 3 significant digits in the concentration. That means we want 3 decimal places in the pH. Okay, put a little star there so we remember how to do that. The number of significant digits in the concentration tells us the number of decimal places in the pH. Okay, so we want to take the negative log of 1.20 times 10 to the minus 3. So negative, push the log button, 1.20 e negative 3. Now, since there are 3 significant digits here, we want 3 decimal places in our answer so that we're showing the precision of that measurement. So 2.921 would be our pH, and there's no units that go along with that. All right, so let's look at the last one. Okay, it says a solution has a hydroxide ion concentration of 1.9 times 10 to the minus 3. Calculate the pH. And there's actually 2 ways that you could do this. Okay, since you're given the hydroxide ion concentration, you can calculate the pOH, and then you can calculate the pH. Or since you're given the hydroxide ion concentration, you could figure out the hydronium ion concentration and then figure out the pH. You're going to get the same answer either way. The second way was probably a little bit harder math-wise to do, but you get the same answer either way. And again, we want to be careful with significant digits. Okay, so negative log 1.9 e negative 3 gives us a pOH of 2.72. Again, 2 significant digits here means 2 decimal places here. But we don't want the pOH, we want the pH. So we're going to subtract it from 14, and the pH is 11.28. Okay, now, since it didn't ask this, but since the pH is less than 7 for the first solution, that makes it an acid, an acidic solution. The second one, since it's less than 7, it's an acidic solution. And the third one, since it's more than 7, it's a basic solution. So let's look at this question. Okay, if we were to look at arterial blood, that just means blood in the arteries. The pH is 7.40. Okay, so this time we're given the pH. We want to calculate the hydronium ion. All right, so we're going to do a little bit of math with that. Well, we know that pH equals the negative log of the hydronium ion concentration. And if we were to look on our calculators, if you look at the log function on your calculator, the second function of that button is a 10 to the x button. That's essentially the opposite of logs. So what we would do, multiply both sides by -1, and then 10 to the negative pH equals 10 to the log of the hydronium ion. We're just raising both sides to the 10 to the x power. And this equals our hydronium ion concentration. So if we're given the pH and we want to calculate the hydronium ion concentration, we would take 10 to the negative pH, and that would give us the hydronium ion. You don't have to ever show all the work that's up here. I'm just showing you how we went from our pH equation to our hydronium ion equation. You don't ever have to derive it though. Just put it in your list of equations. Okay, so there's our equation. Hydronium ion concentration will equal 10 to the negative pH. So in this case, our hydronium ion concentration will equal 10 to the negative 7.40. Okay, so in your calculator, push the second button and then the log button. That's your 10 to the x. Negative 7.40. Now, we're going backwards this time. There are 2 decimal places in the pH. So there are 2 significant digits in our concentration. And it should actually say molarity here. There should be a unit since it's a concentration. There should be an M there. All right, so let's try a couple other ones. Consider a solution of hydrobromic acid that has a hydronium ion concentration of 1.50 times 10 to the minus 3. So we want to calculate the pH. Let's do that first. Okay, to calculate the pH, it's the negative log of the hydronium ion. Now let's see if we can get the significant digits right this time. 3 significant digits in the concentration means 3 decimal places in the pH. So calculate the pH. Okay, so negative log 1.50 E negative 3, 2.824 would be our pH. Now, we know the pH from that. Let's calculate the pOH. Remember that pH plus pOH equals 14. So if we know the pH, we can figure out the pOH. When we subtract, the number of decimal places determines how many decimal places we want in our answer. So our pOH would be 11.176. Okay, hold on to those significant digits because they come from the original measurement. Now, we want to calculate the hydroxide ion concentration. Well, just like we can figure out the hydronium ion from the pH, we can calculate the hydroxide ion from the pOH. So to do that, we would take 10 to the negative pOH. So find that second log button. Okay, that's your 10 to the x. Negative 11.176. Now, because we're starting with the pOH, the number of decimal places in the pOH tells us the number of significant digits in the hydroxide. So 6.67 times 10 to the minus 12. And there should be a molarity here. There should be an M here, just so we have units to go with it.